Okay, good afternoon. Thank you very much for coming to TLN 410, writing a dynamic language compiler in an hour. Quick question first of all, who here has written a compiler before? Okay, so it's about half and half. So first of all, I just want to say my name is Joel Pobar. I am a member of the Common Language Runtime team, a program manager. My features include things like reflection, reflection emit, lightweight code gen, delegates, generics, a whole bunch of the kind of code generation features of the runtime. And I have my compadre here, Joe Duffy. Tell us a bit about yourself, Joe.
So I, like Joel, I'm a program manager on the Common Language Runtime team. My primary focus is on things like concurrency programming models. So that includes the system threading namespace, for example. I also do a bit of work on API design best practices, developing best practices, and then making sure teams within Microsoft are able to actually use those best practices when they write their APIs. You notice actually this has very little to do with actually languages or compilers. It just so happens that I'm a kind of compiler geek, and I enjoy writing compilers on the weekend and nights for fun.
So tell us, why do you think this is an important session?
Well, to me, writing a compiler is the best way to sort of understand every step in the process, from going from a high-level language down to an actual machine architecture. Whether that machine's the CLR, an actual physical processor like x86, and it gives you just a really broad set of knowledge on the services that are offered by the machine and how to take advantage of them. What about you, Joel?
So I like that spiel, but I think the main reason why you guys are here is to debunk the myth that this stuff is rocket science. This is fun stuff. I can't stress how much fun this is. I, like Joe, cook up compilers on the weekends. Not the coolest thing to do, but it's a lot of fun. So this session is all about writing a managed code compiler in an hour. All code, no smoke and mirrors. You're going to get the code at the end of the session. We're going to blog it and put it on ComNet, the code that we actually drag and drop and write today. So without further ado, let's get into it. So the agenda. For the people that haven't written a compiler before, we're going to spend about, say, 20, 25 minutes on the kind of the front end, the architecture of the compiler. So we start with what a scanner is, what the language definition is, what a parser is, what an abstract syntax tree is, and how those things fit together in the front end of the compiler. And Joe's going to be talking about that. And then at the second half of the talk, we're going to be talking about the code generator. That's where I think the fun stuff begins. And not to debunk, put you off or anything, but
right.
The CLR is also a part of that, so we'll be talking about the code generator and the runtime, the CLR itself. And then at the very end, for the last, say, 15 minutes, 20 minutes, we're going to be talking about how to get more dynamism into your language and talk about things like type inferencing, type coercion, all these kind of fun words that guys like Anders Hallsberg likes to spin his wizardry and dazzle you all. Well, we'll tell you all about that kind of stuff and debunk it, not rocket science.
And then you can walk away with those terms fresh in your mind and be the life of whatever party you go to. Everybody will think you're super cool.
Let's
go. Ready to get started?
Yep.
So as Joel mentioned, I'm going to start with the front end. So the front end is generally responsible for taking a language that a user's written, a program, and then turning that into something that the compiler can then turn into executable code, in this case, the CLR. So first of all, you need to know sort of what language you're compiling, right? The language impacts a lot of the design and implementation of the various components in the compiler behind the front end. So you can actually define this formally. This is where you sort of make all the interesting design decisions about what keywords you're going to use, what types of statements you'll support in your language, things like, are you going to do fancy stuff like anonymous delegates, as in C# 2.0. The easiest way to understand a language grammar is actually, let's just take a look at one. So I'm going to switch to this machine over here. And it so happens that we actually wrote a new language. What's the name of this language?
I think it's called Good for Nothing.
Yeah, so it's actually good for something, as you'll see, but it's kind of a toy language. It's not something that you go and productize, for example. So this here is an example of a grammar. You may go through the process of actually writing it down, or maybe you just have it entirely in your head. But the idea here is you say, so right here we're saying our language supports statements. What types of statements does it support? Everything on the right-hand side. So you can have a variable declaration. And you'll notice here, these things in brackets here are actually referring to other components of the grammar. So you jump down here to identifier. You take a look. What is an identifier? Well, it's a character followed by any number of characters or digits. So you notice here we don't actually support digits as the first portion of the identifier, which is actually the case in most languages to make the front end easier, which we'll see shortly.
So what statements do we actually support in our good-for-nothing language?
Well, so like I said, you can do variable declaration. You can do variable assignment. The most complex here is the for loop.
We have a for loop. Excellent.
We do. So this just takes an identifier, sets it to an expression up front, and then keeps incrementing it until it is this expression equal to this expression here. And then upon each iteration, it executes this statement. There's a read integer, so read from the console, print, and then here you have this compound statement. So this is saying that you can actually have multiple statements in our language. So a program can consist of multiple statements.
Well, that's useful.
It is useful to actually write real programs, and they're separated by semicolons.
And so our expressions are strings, ints, and identifiers.
And arithmetic expressions if you want to do plus, minus.
Right. So it's a simple language. It's no C#, but hey, we've only got an hour.
That's right. So let's jump back to the agenda here. So moving on, that was just a quick tour of the language grammar. The next step in the process is actually the scanner. The scanner takes raw input and turns it into something that's easier for the parser to recognize. So what do I mean by raw input? So this could be a file off the disk, so a user program. It could be a user actually typing interactively at the console, like a REPL loop, for example. Most dynamic languages have this. We'll take a look at that later. And what the scanner does is it takes input and it produces a set of tokens as output. And the parser actually uses these tokens to do its job. So in this example that I show up here, we have a simple var x equals hello world. We're setting the variable x to hello world. And then we just print that variable out. And this is sort of a recurring program that we're going to be using throughout this.
So that's good for nothing right there.
It is.
Okay.
And the scanner will take that input and turn it into the second. So it's basically a list of this stuff over on the right, which is a keyword, identifier, literal, etc. So let's jump over and actually just take a look at what our scanner looks like. So first, we have a little bit of scaffolding. Joel said no smoke and mirrors. I don't consider the scaffolding to be smoke and mirrors. It's pretty simple. So we have a top-level program here. And all this does is has a main entry point. And it takes as the first argument the program that it's going to compile. What it does with that in hand is it sets up a new text reader. Okay? And then within that block, it just constructs a new scanner and passes as input that text reader. And then you see down here we have some other things to work with parser and code gen. So then we just have these class files already set up. We have a scanner class, an AST file, we'll see that in a minute, a parser class, and a code gen class.
So these kind of follow the agenda
Right.
slide.
They correspond one-to-one with the major architectural components we showed on the agenda. So starting with the scanner, I'm going to actually drag some code over. So what a scanner does is, as I said, it takes a text reader and turns it into a list of tokens. So the list of tokens is represented by this result here, and we have a list of objects. We'll see in a moment why it's not something more strongly typed. We actually store things like strings, integers, and arbitrary CLR types in there. So we need the flexibility of being able to store anything. So when a scanner is constructed, we just initialize that list, and then we begin scanning the input. And of course, we just have this property here to enable other pieces of the compiler to access it. We have these constants down here, which we'll see how those are used momentarily. But basically, the idea here is that these represent the tokens for addition, subtraction, multiplication, the equal sign, for example. And that's what we'll pass off to the parser so it can generate the AST for that.
So let's see how we scan, hey?
All right. So drag over the scan loop. Remember, this is called from the actual scanner constructor there. And let me just scroll down here. What a scanner does is it just sits there in a loop. And it says, is there a character in the stream to consume? If so, then take it and use the first character in the sequence to determine what to do with the further characters in the stream. So let's drag some more code, which is the meat of this loop. And it's actually pretty simple. So what we do is we look at the first character, And this is an example. If it's white space, the first character is white space, we just skip ahead. Because our language, like most languages, ignore white space. Parsing keywords and identifiers. So if we see that the next character in the stream is either a letter or an underscore, then we know that it's a keyword or identifier. So what do? We construct a new string builder. And this is actually going to hold the contents of the scanned keyword or identifier. And then we just go into a while loop. And this while loop terminates once the next character in the stream is not a letter or an underscore.
So we're just breaking up words, basically.
Exactly.
And it looks like we're adding them to the...
Adding them to the string builder.
Great.
And then at the end, we just add the string builder to the list of tokens. So there's a bit more here. We need to scan a few other things. For example, we need to recognize strings. A string is recognized when we see a double quote. And the nice thing about the scanner and the parser is a lot of it's the same. It's more of the same. You're calling read, peek, turning that into tokens. It's pretty simple. So a string literal, again, it just goes into this while loop and parses until it sees the terminating double quote. Digits are very similar. The one thing to note with digits is that the front end or the scanner actually is responsible for turning that into a real CLR object. So it calls int.parse on the thing that we notice in the incoming stream, and that helps the parser out later on. So it doesn't have to worry about converting between types and things like that.
So I noticed the identifier said that you couldn't have numbers as the first character.
That's right.
So this is why the scanner?
It would become a bit more complex if we enable digits to become the first, because as we've written it here, this wouldn't be able to distinguish between a keyword identifier or a number. So that's actually it for the scanner. Let's just make sure this compiled, and it did. So
no rocket science yet.
Absolutely not.
It's a bunch of while loops. Reading characters. Okay, let's
become very familiar with the I/O library that we have in the framework.
Absolutely.
So the next step in the process is to actually parse the list of tokens. And what this does is make sure that the tokens are arranged in a way that's legal based on the definition of our language. And what it does to them is actually turns them into a so-called AST, or abstract syntax tree, which is sort of an easy to manipulate and work with representation for the rest of the compiler. So an example of that is taking the var x equals hello world print x example that we saw in the previous slides. The parser is taking the scanner's output, which is this list of tokens on the left-hand side, and it's constructing that thing on the right-hand side. So you notice the parser recognizes that we have a sequence. So this is the compound statement that's
the more than one statement.
Yes, delimited by semicolons.
Right.
And what it does is it actually parses those individual statements and stores them in the first and second fields of the sequence statement. And then declare var, obviously, on the left-hand side. That contains the identifier and the expression that you're setting that identifier to be equal to. And then print simply takes an expression.
So why a tree?
Well, a tree, in this way, actually makes it very easy for the back end to either construct new components of the tree as it's doing its code generation. It makes it easier to walk the tree and do analysis, like type checking to make sure that the program's correct, doing semantic analysis, and perform optimization. So you can actually take bits of the tree and plug and play, move them to different areas in the hierarchy. It just makes it easier for the code generator.
Right.
So what we're going to do now is jump back to the code. So now that we have our scanner, we'll jump back to the top level here. And what it does here next is it just constructs a new parser and passes in the constructor the list of tokens that the scanner produced. So let's jump over to the parser file here. Actually, I'm sorry, we need to generate our AST first. So we have a set of AST nodes that need to exist so that our parser can actually generate those. So you see here, AST nodes traditionally map almost identically to the language grammar itself. So it's usually very helpful to have a language grammar handy and actually include it in the comments in your program. So you see here, remember we had a statement, and then down here an expression. So these are the two primary top-level components of our language. And each of those is nothing but an option. So it's a list of options saying a statement is either this, or this, or this. So the way we're representing that in the object-oriented world is actually using an abstract class to be the root of the class hierarchy. So as you see here, we actually have concrete classes for each type of statement we support. So we have a variable declaration here, which derives from statement. And for each component of the language syntax that refers to something else defined in our language grammar, we actually need to use a field to represent that. So you see here we have a string identifier, and that corresponds right to that language grammar snippet right there. And then that's set to be equal to an expression.
Simple enough.
It's very simple. And
so let's take a look at expression.
So let's drag the code for expression over here. Let me scroll up here. So remember, an expression is a string, an int, a variable, or a binary expression, arithmetic expression. And remember that we're actually dealing with native CLR types. So a string literal is actually represented by its string value. An int literal is represented by its integer value. And then a variable is just a string, which, as you'll see in the code generation section, we actually use to look up the value of that variable and determine how to load that when we need to.
So do all languages, say C#, VB.NET, do they have ASTs like this?
Nearly all production languages use ASTs. There are other forms of intermediary representation that you may choose to use in your compiler, but yes, C# does use ASTs.
So one other thing that's interesting to comment on is that we're already defining what the types of our language look like.
Yes. We're saying that actually we're going to represent an integer the same way that the CLR represents an integer.
Right.
And we already made that decision in the compiler. So moving on to the parser, and we'll drag over some infrastructure here. So we have the parser has a list of tokens, remember, that I got from the scanner. And what it does is it positions an index over that list. And then as it goes and parses, it actually increments that index as needed. And then the result of parsing is stored in the result field here. So remember the parser constructed. It does some bookkeeping here. And then the meat of this is actually this function call here, which calls parse statement. You'll notice at the end, after parse statement returns, we actually check to make sure that we consumed all the tokens in the input. If we didn't, then it means that the program was actually incorrect. So there are some tokens at the end that didn't get consumed because it didn't match what we expected. So down here, these are the two primary functions, parse statement and parse expression. So let's drag the code over for parse statement here. And you'll notice there is quite a bit of code here. But as I mentioned earlier, it's a lot of similar looking and similar to write code. First, we just make sure that, yes, there is something to start parsing. We haven't already reached the end of the token list. And then just like the scanner, we look at the first thing in the token stream to figure out what to do next. So you notice this right here. So remember, keywords just get turned into strings. So what we're doing is saying, if this string that we're currently positioned on in the token list is equal to the print keyword, well, we're going to construct a new print AST. So we do that by incrementing the index to skip past the print keyword. And then we construct a new AST node. And you notice we do something funny here. So we expect there to be an expression that we're going to be printing out. So we need to call the parse expression function to actually figure out what that expression is.
So let's take a look at parse expression.
One step ahead of me, man. OK, coming down here. Drag over some code. And it looks nearly identical. We do the same check we did above to make sure we have something to parse. And then if we see a string builder, we know that it's a string literal, because that's the way our our scanner passes off a string literal to the parser. And what we do, we simply construct a new string literal AST node and store the string value in its value field. Pretty simple. Then we return it. And once we do that, we're back up here where we started. And then, sorry for the scrolling here. And then we just store the result of that in the result field and move on.
So why don't we run a demo program, that nice little hello world that we had? Why don't we run that through the parser?
That sounds like a good idea. So I'm going to break point here so that we can actually take a look at what tokens the scanner is giving us. So I'm just going to start.
So we should show them the program we're running through?
Good point.
Yeah.
So it's the same program that we saw earlier. But we actually have put some white space at the beginning here so that we can see the is white space working and test out the compiler a little bit more. But again, it's just printing out hello world. So now that we're in the, we've already started, we hit our breakpoint. So let's take a look at what the tokens are that the scanner handed us. So we have 8 of them. We notice here we just have this keyword var. We have an identifier x. We have this object here, which remember we use that list of constant objects to represent the equal sign. So that's all this is. And then we have an actual string here, hello world. Then a semicolon, then the print keyword, then the X identifier, and the last semicolon. Pretty simple. So let's step through a little bit here to see what this function is going to do. So the first thing it expects to see is going to be a var keyword, which we're at right here. So it's going to step into that. It's going to skip past the keyword. It's going to construct a new declare var AST node. And then it's going to expect the next thing in the stream to be a string. So this is the identifier that we're declaring. So what it's going to do is just take the identifier and stash that in the ident field of the declare var object that we just constructed, and then continue moving on. It expects to see an equal sign there, skips that, and then here, again, it's going to see the expression, and it's going to have to parse that. So let's step into that really quickly.
So all this is doing is really just following the language grammar that we defined earlier, right?
Exactly. And it does so through recursive calls and calls to parse statement and parse expression. So we saw the string literal we expected. We construct a new one and return that. We store that away. And now if we look, we should have a fully initialized declare var instance right here. And notice it has an expression. That should be hello world. And it is. And then our identifier X. So it seems to be working fine. So let's go back over to the slides. And now that we've constructed an AST, let's take a look at how the backend, the code generator, actually turns that into native CLR code that can actually execute.
OK. Now onto the fun part, the code generation.
Come on, that part was fun.
Of course. Right. It's like a movie theater in here. What's going on? OK. So first of all, before we start talking about code generation, it makes sense to understand what we're code generating to, what we're targeting. And for this, well, of course, we're targeting the CLR, Common Language Runtime. So it makes sense to understand how the CLR actually executes code. So the CLR is a virtual machine, and it's actually a stack-based virtual machine that goes away and executes something called IL, intermediate language. And intermediate language was defined by a bunch of Microsoft geeks, a bunch of commercial compiler guys, a bunch of academics. They got in a room, they thought it out, and they came up with a language, a stack-based language, to be language neutral. So most language, from functional, dynamic, static, OO, you name it, could target the CLR runtime and have nice kind of language interop between them. That's how you get C# calling into VB and so on and so forth. So let's take a look at what this language looks like. I have on the screen a 10 plus 20 minus 5 expression. And underneath that, I have IL. And on the right, I have an evaluation stack. Now, if you think back to good old Comp Sci 101, everyone knows how a stack works. Push, pop, execute, etc., etc. So no big dramas there. So let's see, kind of walk through what this would actually do. So I've got the first IL instruction, LDCI4, and LDCI4 means load me a int32 with the value of 10 onto the evaluation stack, please. So as you can see on the right, the evaluation stack has now got a 10 on it. Load LDCI4 20. Load the constant 20 onto the stack, please. Now, finally, this is where we actually add them up. We want to execute an add instruction on that guy. The add instruction, thanks. The add instruction, its invariant is that it will pop two elements on the stack off the stack, add them together, and push on the result. Now, this ain't rocket science. I want to do subtract 5. So again, I push on the value 5, and I execute subtract. The result is 25.
So wait a second. What you're saying is that when you're targeting IL, you don't have to worry about things like register management and other things that actually targeting native machine code. You
Absolutely. So you don't have to worry about stack frames, function call stuff. No, none of that infrastructure. It's all kind of based on the stack.
Excellent.
So to check to see what other IL we can look at, you can actually use a production quality compiler like C# and write an expression in C# and see what it evaluates to. So I'm just going to quickly show you a demo on how to do that. I've got a little command line window here, and I've got a nice little C# hello world application. Pretty standard. It looks quite similar to the good-for-nothing language. Of course,
Except our language is a little less verbose. You know, you don't have to declare a type or a method. You just write the code you want to write.
I'm glad you noticed that. We should ask Anders about that. Okay, C#, hello world, .cs. I have a .exe out there. I can run it. Nothing too exciting. Hello world. Great. I have this tool called ILDASM. And this tool basically decompiles the assembly into its type, assembly, and module infrastructure. And, of course, the IL, which is the interesting part. So you've got my foo type here, which has a bunch of methods, constructor, and, of course, the main method. So if I look at that, I see more IL, similar to the previous slides. So what's it doing here? We have a no-op instruction.
What is that?
So who can yell out? Anyone know what the no-op instruction is used for? Nothing. Okay, well, as it turns out, it is used for something. In debug code, C# emits a no-op instruction for every curly brace. And the reason why we do that is because you want to hit a breakpoint on the guy.
Our compiler doesn't do that, though. We don't have curly braces.
No, we don't have curly braces.
We do have semicolons, though.
We do have semicolons. So that's what no-op instruction can be used for, but otherwise it's just don't do anything. LDSTR, load string. Load me a string hello world onto the stack. Store lock. Store the local. If you can see here, we have in IL, you can define locals for a particular method. And I'll show you this in a slide or two. Load that local, and then finally a call method, which takes as its argument a method signature, system.console.writeLine, passing in a string. So this, the invariant of call is that it will pop off the argument. So in this case, it'll be a string. And it will call the writeLine method, passing as a parameter the argument that we just popped off the stack. And then we've got a ret function, which means it's verifiably OK to return from this method. Now, if the method is void, then the runtime expects that there'll be nothing on the stack. If the method isn't void, say it's something else, then, of course, we expect something to be on the stack, and the ret instruction simply returns. I'll answer questions at the end. Sorry about that. OK. Pretty simple stuff. So let's keep going. We kind of just briefly saw the storage aspects of the IL. We can store into locals, and we can store and load from fields in a class. I think the interesting part here is the fields. So if I say I load string hello world, and I want to do a store field, I say I'm going to store a string into foo.f. And the runtime can then verifiably make sure that foo.f is actually a string before it assigns it into that field. Okay, IL also needs control flow. Makes sense, right? We need to do our for loop. So I've got here a if-else statement, just as an example, and this is kind of the typical code that a C# compiler will emit. Nothing too fancy here, not rocket science at all. We have if A, so assuming that A is a local, well, okay, I need to test to see if that thing is true. So I load the local on the stack, I load a 1 onto the stack, and 1 is the equivalent, it is an alias for true, 0 is false, and then I do a compare equals. So I check to see, is this thing true? Tell me yes or no if it's true. So compare equals will say, well, okay, 1 equals 1, so I'm going to pop those two guys off the stack, push on a 1 as a true. Now I have the first control flow opcode, which is branch if false. So if I see a 0 on the stack, then I want to branch to another label, IL00020. If I don't see a false on the stack, then I'm just going to continue executing. So 10 and 11 will execute. And you'll see 11 is branch to 25. And 25 is the rest of the method. It makes sense because I don't want to execute the else statements.
So there's a number of different variants on the branch instruction, right? So you can branch if true, you can branch if less than or greater than, for example. There's probably 10 different branches that you can choose
Yes, absolutely, absolutely. Pretty simple stuff. OK. How do we generate code? We've got this nice little parse tree with nice AST nodes that Joe has kindly given us. Now we want to actually emit this IL and all the plumbing and the infrastructure to emit a .exe or a .dll .net assembly. It's a lot of dots. Okay, so we ship as part of the base class libraries a namespace called system.reflection.emit. Can I get a quick show of hands as who's used reflection emit before? Wow, okay, about half. Excellent, so I'm going to go through what these APIs look like for the other half of you. On the left-hand side, I've got a piece of C# source. On the right-hand side, I've got the reflection emit APIs that are needed. To emit a .NET assembly, I first of all have to have an assembly, I have to have a module, I have to have a type, I have to have a method, and I have to deal with some locals. So reflection emit has these things called builders. So it's a assembly builder, module builder, type builder, etc. to go and do that plumbing and infrastructure for you. There's also two other important classes, IL generator, which is a method to emit IL into a byte stream, and opcodes, which is a struct that has every opcode we have in the system.
So basically what you're saying is you don't actually have to remember the binary encoding of the file you're outputting, nor do you have to remember the binary encoding for every single instruction that you need to emit.
Right.
It's all there for you.
It's all there for you. Reflection emit takes care of it for you. Which brings us on to the code generator, finally. So let's jump in. Okay, wrong one. Okay, so code gen. Nothing in here so far. So I've got to drag and drop a couple of globals. We have our IL generator, and IL is going to be used for the rest of the kind of the session, or the code path. I also have a thing called a symbol table, which is a dictionary which resolves a string to a local builder. So can you guess as to why I'm going to need that?
To store your symbols?
Right. So all those var x that we saw, that x is actually a string in the parser. So what we need to do is say, well, we know that variables are going to be used for storage, so we need to then choose what kind of storage mechanism we're going to use. In this case, we choose a local builder.
So what if you had types and you wanted to actually reference fields of your object, for example?
Absolutely. So if you wanted to get a bit more extravagant, say like the C# compiler, then you would have to have a more complex symbol table that resolves kind of scoping rules, as in where a variable is actually visible, to a more complex data structure like, say, a field builder, a local builder, whatever storage mechanism is for that particular scope.
See.
Okay. Drag and drop the constructor. Nothing too interesting here other than we get that statement, that first sequence statement that Joe passes us, and we also get the module name. And we get that from, of course, the main program, which I'm going to uncomment now, just creating a new code gen, passing in the result of the parser, and I'm passing in the file name without the extension. Then the rest of it is just basically plumbing. We're using a bit of C# aliasing for those of you who have not seen that yet. We're basically saying in the using statements, collection is an alias of this namespace. Okay. So I'm saying, okay, give me an assembly builder, give me a module builder, give me a type builder. I'm kind of cooking up this stuff, and it's basically 4 lines of code to kind of get the meat of the PE file that will eventually be emitted. The only interesting thing here is we pass in the name to the assembly builder, and we also say, I want to save this assembly. The other option in reflection emit is that you can generate code into memory and not actually save it, and then invoke it via reflection from your code.
So I know some people, complain that you can't actually unload the code after you generate it. Is there any solution for that in WDME?
Common request. I use reflection emit to generate code in memory to say do a domain-specific language, and I want to generate that code and then throw it away. Yeah, we didn't have a solution for that in v10 and v11. That code would just kind of stick around forever for the lifetime of your application. We do have a new feature called LCG, or lightweight code generation, which I will show you guys towards the end of the talk, which is absolutely reclaimable, by the way.
By the GC, correct?
By the GC.
Right. Before 2.0, you could actually generate code in a different app domain and unload that app domain specifically or explicitly, and that would dump the code.
Yeah.
But usually you want to generate code in your current app domain, so that wasn't a great solution.
So the type builder, I'm saying, hey, type builder, go and give me a method called main. Whoops, sorry about that. And have it be a static method returning the type of void and has no arguments. Pretty simple. So I've got my main method. Now I actually want to go and generate code on that main method. So I say, hey, method builder, give me an IL generator, please. I'm ready to go start compiling some stuff. Our main method, gen statement. I'll just drag and drop the rest of the the infrastructure stuff. Nothing here interesting other than the set entry point. So whenever you run an application for the first time, that sets a metadata bit in the assembly to say, this is the method that you're going to run first. OK, so let's go and have a look at gen statement. Drag and drop that guy in the class. Oops. This really is on the fly. And the first thing that we're going to get, if this runs and compiles, see how I notice how I put the breakpoint on the curly brace there? Pretty nifty stuff. We're going to jump past the parser. First thing I get is a sequence statement. On the first, it has our declare var, like we noticed in the slide. On the second, it has the print. So if we just kind of walk through that, the idea is to generate the first, the left-hand side of the branch, and then, of course, the second of the branch. So we're just going to do a recursive call, jump back in there. Well, now I've got a declare var AST node, so now I need to go and generate some code for that. So let's go and do that. OK. If the statement is a declare var, now I'm using my symbol table. I say to the symbol table, I basically ask my IL generator, this is the first time that I'm going to declare a variable, so please go and get me a local builder, thanks. So reflection emit says, OK, you need a local builder. Well, I need to know what type that local builder is going to look like. So I have a nice little helper method here, type of expression, which I'm going to drag and drop down here. And its primary job is to go off looking at an expression, AST node, and tell the reflection emit what type it is. So if it's a string literal, then return type of string. If it's an int literal, do the same for int. I mean, all pretty simple stuff until we get to variable. So when we get to variable, we ask the symbol table, hey, do you have this variable declared? Yes, I do. Maybe I don't. Go and ask that symbol table to get me the local builder. And then from the local builder, I say, hey, local builder, what's your type? So pretty simple for type of expression.
So you're telling me that we actually infer the type. We use local variable type inferencing. Aren't the C# guys looking at something like that?
I'm glad you said that. So this is not rocket science at all. We're basically doing type inferencing. So var x, it has no type. I didn't have to say string x. Less typing, I think. I mean, it would be great if we just nailed that var word altogether, but I say you guys should go and talk to Anders about that, see what's going on. Doesn't seem like a whole lot of work to me. OK. So I've generated code for declare var, and the first thing that declare var does is say, well, I've declared a variable using a local builder. Now I need to assign something to it. That expression, so var x equals hello world being the expression, I need to assign that to my variable. So I can just do a quick bit of AST munging, cook up a new AST node, which is the AST node assign, put the ident in there, and put the expression in there, and then just call gen statement to go and generate code for the assign statement.
So this would be pretty difficult to do if all the front end handed you was this list of tokens, if it didn't generate that nice, easy to work with abstract syntax tree.
Absolutely. So that's the reason why we have the parser. OK, so assign's job is to gen an expression onto the IL string. That's his first job. So why do we need to do that? Well, if you think back to the stack, if we needed to do, say, 1 plus 2 or assign something to a local, for example, like we showed you before, I first of all pushed on the string, and then I called store lock as the second IL instruction. So I'm going to do that first. I'm going to first of all generate the expression. So now if I drag and drop generate expression, it has an expression and an expected type. Now, expected type will become important soon, and we'll show you why. But gen expression is pretty simple, and this is the first time we've generated some actual code. If it's a string, go and emit into the IL generator the opcode, load stir, and pass in it the value. So I'm just kind of picking off of that AST node. Using opcodes, picking off of the AST node, pretty simple. So we finally generated some code.
So we went through all of that, and this is the first line of code we've actually generated?
That's true, that's true. But it is kind of repetitive. So we have some more code in gen expression. We need to deal with some variables as well. And it's the same kind of deal. If we need to assign, say, a variable to a variable, well, first of all, we need to push that variable onto the stack. So you can see here we're using load lock. And we're passing the local builder. And that's why it's nice to have that symbol table from ident which is in the AST, to the local builder, which reflection emit deals with nicely.
So you don't pass the name of the local to the load lock. You actually pass the local builder.
That's correct. That is correct. Okay, so store. We need to go and store this thing. Well, I don't think this should be too hard. Store is pretty simple itself. It first of all says, okay, what's the name that I'm going to store to? So the identifier, basically. And what's the type? And this becomes important later as well. It then asks the symbol table, get me the local builder with this name, and then emit a store lock. Nothing complicated, no rocket science yet. All right, so I think we've emitted all of the AST nodes in order to run our first program.
I actually think you should uncomment the line that calls the store function.
This is why I have you up here. This is great. Excellent. Build succeeded.
Now we're ready.
Okay. So we're going to, first of all, step through and just show some of this code generation happening. So I'm going to walk through. This is compiling the Hello World example that we've always had. So I have the first of all the sequence, and I want to go and generate the first in my sequence. So that's on the left-hand side of that nice little semicolon. Okay, I have a declare var, finally. As you can see here, statement is a declare var. And in statement, I have my string literal hello world. And I have my identifier x. So let's go and first of all declare the local, but I have to step in and ask my little helper method, hey, what is the type? And of course, hello world is a string because the parser said it was a string. Excellent. I just return the type of string. So I'm using a bit of reflection there. Then I cook up my new assign statement to assign hello world to x. So I do that, and then I bolt back into gen statement, kind of like recursive descent, which is a code generation, parse technique and code generator technique. And now I have an assign in my hand. So let's go in and generate an expression. First of all, I have to ask what is the type of the expression. This becomes relevant later on. It's a type of string. Okay. Now generate the expression. If the expression is a string literal, I set delivered type to type of string. Again, becomes important later on. And then I emit my first line of code. And we're done. And then I emit the store. I just go in, ask what the type is again, and jump into the store method, ask for the local builder, which is there because I've already defined my local, finally. And I then emit a store lock. Now, I won't go through print because we can see what the code gen looks like with ILDASM. So I'm just going to finish this off, let F5 and go all the way through.
So you actually generated code. You didn't, this isn't an interpreter that actually just ran the program. Although, as you watched you step through it, you could implement an interpreter very similar to that.
I could implement an interpreter very similarly, but I actually generated code. And as you can see, I have my Hello World GFN good for nothing Hello World program. That's it there. And I have hello world.exe. All right, drum roll, please. Fingers crossed. Our first piece of generated code.
Oh, no. What's up with that?
What did I forget? Who said it? Oh, wow! This is totally on the fly. I'm telling you. Thank you very much. Forgot to implement print. Come and see us later. Yes, the kind man in the audience was right. We forgot to implement print, and all print does. Man, that was a letdown. Okay, generate expression. IL emit. Opcodes.call to system. I'm using reflection here. Go and ask for system.console. I'm getting the method writeLine, which takes a parameter string. So yes, we now have that as the code generator. Let's build and succeeded. Okay.
Drum roll again.
Good for nothing compiler. Hello world.good for nothing. All right. Yes, there we go.
Very good.
Okay. Fair enough. It's pretty much good for nothing. Let's take a look at the ILDASM though. Hello world.exe. I have my food type there that I declared with my type builder. I have my main method that I declared with my method builder. And I have the load string, the store lock, the load lock, and of course the print that I failed to do at the beginning, and of course my ret and the ret came out of the end of the plumbing infrastructure of the constructor.
And no ops, because we don't have curly braces.
No ops. Okay, so let's do something a little more interesting. We'll drag and drop the rest of the code for the rest of the AST. Actually, let's see if we can break this compiler first of all.
How might we be able to do that?
So let's go in and say, well, what if this were a 10?
Yeah, didn't our language grammar say that was a legal program?
Absolutely, absolutely.
Okay.
So let's good for nothing compiler, hello world.good for nothing, and then run it again. Got an exception. Can't be good. The exception's completely crazy. Don't know where that came from.
No
but
reference.
Yes, I have no idea. But what we do, we do have a tool that detects bad IL. One thing that reflection emit doesn't give you by default is bad IL detection. So there's a tool that comes with the SDK called pverify, hello world.exe, and that goes and analyzes the IL to see if there's anything wrong with it. As it turns out, we have here, at IL offset 7, I found an int32, but I expected a system.string. Unexpected type on the stack. So let's take a look at hello world.exe, go to number 7. Well, okay, I guess it is expecting a string, and what we loaded on it was a local that was of type int32. Okay, so we've obviously got a problem there. That completely annihilates the CLR verifier. The CLR will not let you do something like that because the types aren't compatible. We're all about running safe code. But what we can do...
And note, we didn't have to actually see an access violation and then scour a memory dump to try to figure out what was wrong with the program. PE-verify is definitely a managed compiler's best friend.
Absolutely. Okay, so we know that the gen expression has this thing called expected type. And if I go up to my print statement, I'm passing to gen expression the expected type of string. Okay? So if I go back down to gen expression, I can say, well, my delivered type is the type of, like, say I get to my int, which is exactly the code generation I'm doing for my var x equals 10. I'm saying the delivered type is now type of int. And then I go and emit that int onto the stack. What I can do down the bottom here is this. Check to see if the delivered type and the expected type match. If they do, good as gold. Don't have to worry about it. If they don't, what I can do is generate some more code to convert the int type to a string type. So the delivered type to the expected type. And this is a feature called type coercion, which is popular in dynamic languages, and also something that, that maybe the VB.NET guys or the C# guys could look at implementing. Actually, I believe the VB.NET guys do actually implement this. So what we're doing is saying, well, I've got an int, I need to convert it to a string. Let's just box this guy up. And boxing, it means take a value type that's on the stack, wrap a method table around it, and put it on the GC heap in order for me to call methods on it. So that's all we're doing there, boxing it up, putting on the GC heap, and then calling, using the callVert method, which does a virtual call, the method toString, which the invariant is it returns a string on the stack. Good as gold. Build succeeded. Good for nothing compiler. Hello world.good for nothing. Hello world.exe. Good as gold. Yep, thank you. Type coercion in a nutshell. What, 5, 6, 7 lines of code?
It turns out some compilers are more liberal in the type coercions they'll perform, like, for example, only doing widening conversions. Static type languages seldom do the type of coercions we just showed you, but dynamic language compilers do.
So dynamic language compilers do this all over the place. I mean, they'll try and convert, you name it, to whatever you want and see how it goes in a verifiable fashion. So let's just drag and drop the rest of the gen statement. We'll take a quick look at, so I've done the read int and the for loop here. We don't have to look at this. The source code will be available, so you can look through this yourself. I think the interesting one is the for loop. Nothing much to it. We're doing a bit of AST cookup creation, doing the same gen statement thing on that assign. That's to do the x equals 0, so for x equals 0. And then we're using the typical mark label, which does label marking in IL to allow you to do the jumps that we talked about before. So the branching, and flow control.
So we could use the same thing to implement if statements in our language, for
Absolutely.
example.
In fact, the code would be very similar. Okay, let's compile that guy. We have our full good-for-nothing compiler, but let's kind of stress it out.
But hello world isn't stressing it out?
No.
It's good for something then.
Okay, so let's use some loops and some printing to the screen, and we'll read in an integer, say. So loop.gfn. Okay, so I need to declare a variable because I need to get how many times I want to print something. So var n times equals 0. So what do you want me to print to the screen? We're going to ask a question to read in a number.
How much do you love this company?
Okay. How much do you love this company?
And we'll accept values from 1 to 10.
Okay. 1 to 10. Now I can read in an integer, read int n times. And now I can then go off and perform a loop to go and print something out. So for x equals 0 to n times do, what am I going to print?
Let's see. How about developers?
Developers. Okay. End the for loop and print something at the end for good measure.
Who said sit down?
Okay. Looks like our program's complete. Looks good. Good for nothing. Save it. Exit out. Got my loop guy in there. Good for nothing compiler. Loop.gfn.
It worked.
And let's have a look. Loop.exe. How much do you love this company, Joe?
11.
11. Developers, 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 developers.
Come
and
on.
Then who said
a little more
out?
enthusiasm. So that's a famous quote, right?
That is a famous quote. Our extravagant CEO likes to jump around quite a lot and say things like that. Okay, so that's it. Our compiler is pretty much done.
Excellent.
So let's see, we'll go back to the slides and talk about how you guys can go away and extend it. So we've had a look at the good for nothing compiler demo. Going further, so the stuff that we didn't show you, which is going to take a little longer than, say, an hour to go and write, function calls. Well, of course it makes sense. You want to be able to call into the base class libraries, so that's kind of important. So there's two ways to do function calls. There's a static way, where the compiler knows at compile time, say at the parser or at the code generator level, what that method is. It knows it can just slurp up an assembly, it can resolve it and says, yep, I know exactly where that method is. And there's also a dynamic way to bind to these methods. And so VB.NET is a great example of where dynamism comes into play in terms of function calling. So I have a piece of code there, option strict off, and that turns on something called a late binder. Dim obj, I don't type the thing at all. And then I go obj.method1, bracket, bracket. I haven't declared a method 1 anywhere. The compiler simply says, you know what? I'm going to defer the matchup of the type and the method as far late as I possibly can. And then I will execute it, say, at runtime. So the IL that emits is load me a local obj, load string, method 1, a whole bunch of other goop and gawk. You can actually look at this using ILDASM. And then it calls something in the Microsoft.visualbasic.dll assembly, which is part of the Visual Basic compiler. And it is actually loaded with your VB apps when you have an option strict off. And it calls the late binder to do a late call. So what does that thing look like? Well, here's a simple late binder. My late binder takes an object, takes a method name as a string, and takes a list of arguments. A simple late binder might do something like this. Go and get me the type of the object, and go and get me a method with this method name using reflection. I now have in my hand a method info. Now I just want to invoke it, passing in the obj as the guy to invoke on, and passing in the arguments. Pretty simple.
So a real late binder probably might do things like error checking to make sure that the right number of arguments get passed, maybe even doing some coercions in the process, and this could fail.
Absolutely,
right?
This could definitely fail.
If method name wasn't defined on that type, we would have a missing method exception, which is probably a suboptimal experience for the user.
So for example, if the method was missing, I could do something really dynamic, like say on error resume next. Kind of say, well, you know, I threw reflection threw an exception, so let's just kind of execute the next line of code and just don't worry about it. A late binder could definitely do that. It can do type coercion out the wazoo as well. So that's dynamic late binding, used pretty much everywhere in dynamic languages like IronPython, which I'll show you in a second, and other languages like, say, Lua. Okay, going further, real dynamism. If you want to get that kind of really dynamic experience, we did a lot of type coercion and type inferencing. What you could do is just say, make everything object. I mean, we need to go at the root of the CLR object hierarchy, and that's, of course, system.object. So what if we make all our storage locations typed as object? So then I could have an interesting expression or statement like this. Var x equals, hello world. On the next line, x equals 10. And x could be both a string and an integer. And then my late binder could resolve and deal with the dynamism of that type at runtime. So it knows about those types at runtime. Another thing you can do is the read eval print loop. And I've got enough time for a demo, so I'm just going to quickly show you what a read eval print loop actually looks like. Okay, jump into IronPython. So who here knows about IronPython? Okay, so about 20% of you guys. So IronPython is the Python language for .NET written by the CLR team, originally written by Jim Huguenin, and we actually got him on board to lead a team to go and write a Python implementation for .NET. And it uses a REPL loop, which is a nice little fun way to kind of dynamically create a program on the fly. So I can do things like 2 + 2, and it gives me 4. Print hello world, hello world. And I can define functions and invoke those functions, et cetera, et cetera. And this code is being generated in the background, and I can refer to it at any point in time. So if I create a method and then use it later on in my REPL loop, it'll still be there.
So it's not doing interpretation, although some REPL loops do interpret.
Right.
It's actually generating CLR assemblies in the background.
Absolutely. So one of the key things about IronPython is that a lot of the time this REPL loop experience is interpreted. But with lightweight code generation, that's problem's kind of solved. So if you want to learn more about IronPython, there is a session that we'll show you at the end to definitely go to. It's going to be a fantastic session, and there's a good 25-minute demo on the power of IronPython and how it can help kind of create these dynamic applications. So let me just quickly get out this and go back to the slides. Cross-language interop is another thing that you're going to have to think about. So say if you have this real dynamic experience and everything is typed as object, then you're going to have to interact with this statically typed BCL. We have this nice BCL that guys like Brad Abrams have come up and they've cooked up. It's nice, it's great. So like, for example, our write line, which takes a string, there is actually an overload that takes an object, but for the purpose of this conversation, cross-language interop. If everything is typed as object and you need to pass it to BCL types that expect something else, then you need to kind of get this dynamic type coercion going on, and you can do that in the late binder. Okay. The other important thing about the cross-language interop is if you're generating code, so say you're generating methods that are all, the signature's all typed as object and it's returning object, then a static compiler like, say, C#, when you go to load that assembly and kind of look and want to invoke those kinds of methods, IntelliSense experience is going to be all typed as object, that kind of thing, and it's not clear how that will mesh. So it's a tough problem to actually think about, mapping the static and dynamic type systems together.
You don't want your users of your language, say if you're generating reusable libraries, to have to do all these typecasts just to interact with your programs.
Exactly. So what is LCG? I'm going to give you a quick kind of run through of it. LCG is, as I said, the solution to the reflection emit, my code won't unload problem. Give me back my memory, please. And it is basically dynamic methods generated on the GC heap at runtime. All that assembly and type plumbing infrastructure that we saw in reflection emit, all gone. Don't need it. As you can see there, it just uses one API called dynamic method, and that sits on the system.reflection.emit namespace. And you can see it looks a lot like reflection emit. We're using an IL generator. We're using the same emit and opcode structures. Pretty simple stuff. Again, this is going to be shown off in a future talk that we'll show you at the end. The other interesting thing is that dynamic methods, or LCG methods, skip JIT time visibility checks. Okay, so what does that mean? You know, whatever. Private reflection. I love it. A lot of people hate it. This goes one step further. The JIT doesn't even care. You can poke into anyone's private members with these. The JIT will just say, yep, no problem, we'll give you this. Of course, this is only in the CAS. There's certain CAS security issues around that. If you're in full trust mode, this works fine. If you're in like a semi-trust mode, then no way. But it's still a cool feature.
And to be fair, there are some scenarios where LCG can't be used. For example, if you need to generate types, you're still going to have to use the reflection emit namespace, because LCG right now, there is no LTG, lightweight type gen.
Right. So this LCG, so if you think back to the REPL loop that I showed you before, the 2+2, what IronPython is actually doing is generating an LCG method. Yes, I know it's disgusting, but it's generating an LCG method to load 2 on the stack 2 times and then call the add instruction. But it's fast, and that's the key thing.
Okay, so there are some other advanced language features that you might want to support that a lot of dynamic functional languages have. For example, closures. Being able to actually write anonymous methods, for example, in C#, it's a form of a closure. So what the C# compiler does is takes the lines within the method block, and then it generates a type silently for you, a new method, and hoists that code from outside of within the method into its own method itself. And then what it does is constructs a delegate to refer to that thing. And delegates are sort of the CLR's way to deal with first-class functions, where you can pass around basically typed function pointers to other people to invoke later on. And this is really what the eventing subsystem in the CLR is based on top of. There's some other interesting design points there too, where you can actually capture variables that are accessible within a scope. But unfortunately, once you hoist that method out onto a generated type and method, you know, it may not be accessible any longer. For example, if it were a local within the method that you wrote the anonymous function within, you actually need to do something called a closure conversion, which hoists those locals out onto an instance of an object that the closure has access to. Now, this is pretty complex, but if you actually go, this is another area where ILDASM comes in very handy. You write the code in C#, you ILDASM it and see how they did it. It's some pretty interesting code generation patterns there. Another one that's even more complicated than that is iterators. So in C# 2.0, you can actually basically create an enumerator by writing yield statements. And this is almost like you're returning from the middle of a function, and then you're resuming later on. So if you're familiar with coroutines, which are implemented in some other languages, this is similar to it, although not identical. There are some limitations there. But if you ILDASM C# 2.0 code again, it's pretty interesting what they do. They actually do a state machine transformation on your entire method within the iterator. And then your code doesn't look anything like what it used to look like when you wrote it. So this is one of the more complex patterns that you can implement in your compiler. And then, of course, there's commodity stuff that we didn't show you, like good error handling, throwing an exception from the middle of the parser or the code generator, telling you, error information without source, like line level, what line in your program the error came from. And also, some compilers will actually do sophisticated techniques like trying to move ahead in your program to find as many errors as it can before it bails. Because it's obviously annoying if the user is trying to compile a program with lots of errors, and all they're getting is 1 error at a time. You can imagine 100 errors in a program. They have to try to compile, they get 1 error. Fix that, try to compile, and so on. So that's the kind of stuff you can do. And the line information comes in handy for generating debug symbols. Actually, if you write your code correctly in CodeGen to emit the debug symbols along with your IL, you get debug experience in Visual Studio for free. So you can step into your own programs, and it will show you the original source in your language. So that's another fairly simple thing to do.
In fact, I think it's only 3 lines of code.
Yeah.
If you hooked up the scanner properly, it's only 3 lines of code to get reflection emit to generate PDBs.
And of course, the last item on here is resolving dependencies. So oftentimes, programs are going to rely on third-party libraries that we ship in the framework. Like, say you want to use system.xml in your program. You'll have to worry about, well, what technique do I use? Do they have to declare what their dependencies are? Do they pass it in the command line to the compiler? Or do we do something intelligent, like scanning every single framework assembly on the machine to see if we can find the namespaces they're referring to? So that's actually it. We'll go over some resources here. The first one on the top here is an awesome book, actually written by Joel's professor from college,
Yep.
from QUT in Australia. And it's essentially takes you through everything we've talked about and more with tons of great examples. It's an awesome book. I highly recommend it. It's actually fairly easy reading as well. The second one on here is Inside MS.NET IL Assembler. So this is actually a tour of the instruction set. So using this, you can figure out some pretty nifty code generation patterns and really understand every single instruction in detail, if that's the kind of thing you're interested in. The last one here is a classic book. It's called the Dragon Book. And this is more of an academic compiler book, but it's, like I said, it's classic. It's basically used in almost every compiler course taught in universities.
Does anyone see the movie Hackers? In one of the scenes of Hackers, it was pretty lame movie, but one of the scenes of Hackers, this crazy guy is kind of pulling out all these freaking manuals, these hacking manuals, and all that kind of thing to show how cool he is, and he actually pulls out the Dragon Book in that scene. So, very cool book.
It's a movie from the early 90s where computers are very Star Trek-y. Highly recommend it.
Okay, some other books. Shared Source CLR Essentials. This is the Bible for the CLR. We actually ship the CLR source code in a form called Rotor. It's downloadable. It's actually cross-platform as well. It has a academic-friendly license, a hobbyist-friendly license, and you can run it on FreeBSD, Mac OS, and of course Windows. This book kind of walks you through the source code of the CLR. So if you're interested in kind of the more under-the-hood stuff, I definitely recommend getting this book. It's an excellent book. The CLR annotated standard. Jim Miller is an architect on the CLR team. He took the ECMA spec, which is kind of the specification we use to define what the CLR is, and annotated. So you can imagine that it's all the specs for the CLR annotated to make it kind of easier to understand. And of course, Joe Duffy's book. I love this. There's the man himself. Joe up on stage. He wrote a book about the .NET Framework 2.0. Come up and get one of those. You can sign it if you like. I think it's hilarious. Comes out in February, I believe.
January, February next year, yep.
Great.
I just finished it before I came out here, so I'm very excited.
Okay, resources, other talks. The CLR Leveraging Dynamic Language Features talk is going to include things like IronPython, LCG, and some of the really cool new kind of VB.NET dynamic features that we talked about. I'm not going to give anything away. I think it's an excellent talk to go to. VB is the new black. I tell you now, the new black. I love it. Definitely go to that one. And also IronPython will be showed off there. IronPython actually ships as source, so you can download it and go toy with it and play with it. A lot of the concepts that we saw here, you'll see reflected in the IronPython source. VSIP, something that we didn't talk about, Visual Studio Integration Package. Take your compiler and integrate it into VSIP. So get IntelliSense, colorization, all that kind of neat stuff. You just have to make some tweaks to your scanner and parser to get the VS.NET to hook up properly so VS can ask your compiler questions. Hey, should I colorize this token? Should I do this? Should I do that? VSIP's really cool. Also, my blog. You know, everyone's got a blog these days. I'll just add to the millionth list. Joe's blog. Cool mailing list to get on is the .NET Compiler Developers mailing list. We're both on it. Most of the CLR team is on it. Jump on there and say, you know, I'm just kicking around. I want to do some hobbyist kind of compiler coding. Can you guys help me out? And we'll be for sure, absolutely, we'll respond to your questions. And you can even do it with the source code that we're going to give you today. And of course, a list of .NET languages we have available on that side. That's it for us. Please do fill out the speaker evaluation forms. We do want to become better speakers and kind of make the session better. So please fill it out. I believe you win a prize, I think. Go to those other sessions that we talked about. And if you have any questions, come up and see us. Thank you very much for coming to the talk.
Thank you.